slow down and savour the mathematics. No, sorry about that. I can't help myself. I'm a biostatistician. We have to make it painful for you. Okay, what I'm going to do is I'm going to now get to the practical end of using these models. And for me, when I first learned about these models and I saw this is where they made sense to me. So we're going to consider two different types of linear mixed models, okay? And I want you to remember that mixed models are subject-specific models. What do I mean by that? I mean that every individual in our sample has its own regression equation. That's what subject-specific means. The first is the simpler of the two models. We're going to call it the random intercept model. So in other words, we are randomly sampling the intercept from a population of intercepts. Think about it like that. So each subject is allowed to have its own baseline value, okay, for example, of reaction time when it comes to sleep data. They're allowed to have their own baseline reaction time, but their response to sleep deprivation is assumed to be exactly the same. Okay, so we'll have a look at a graph and hopefully it'll make a little bit more sense. In other words, all of the subjects will share a common slope, but they're allowed to have their own intercept. So this is a nice simple model. This Z matrix essentially is a column of ones, so it disappears. And we get something that looks like this. Here's our random intercept model. Y equals the fixed effects plus some value that is subject specific plus the error term. Okay, so just defining those terms exactly how I did before, I'm going to skip this. The important thing to note about this is we have the fixed component as normal, and we have a random component that is a simple change in the Y at the intercept due to that subject. Let's do a little rearrangement to make this a little bit clearer. So, just being explicit here, here's our full model. These are our fixed effect, and then we have the random effect. I'm going to just simply move that random effect, because it's a constant, up to here. So, subject I, sorry I've got an extra Y equals there. So subject I has the intercept of beta 0 plus UI plus the standard fixed effects, where UI is the difference from the average intercept, beta 0, due to being subject I. In other words, some people are higher at baseline, some people are lower at baseline, and that should be a normal distribution around beta 0. So now let's fit this. Let's run this model for our sleep data. Now remember, in our sleep data we want to investigate the effect of sleep deprivation on reaction times. On day 0, the subjects had the normal amount of sleep, and then they had 3 hours sleep for 9 successive nights after that, and we want to see the effect on reaction time. And we'll start by running our random intercept model. Okay? First of all, particularly the more complex the data gets, the more important it is to eyeball the data. Use our eyeballs and look at it. So here we have day, here we have reaction time. That doesn't tell us too much. Let's use a line to actually relate the observations by a different subject. So here we have the trajectories for each subject as we go over time. We see some people, it almost had no effect at all. I think they might have been sneaking some sleep in. So their reaction time was good, and basically it was good after 9 days of sleep deprivation. Some people it was horrible, basically. They fell apart. Okay? So now we're linking the within subject observations. Also note in this particular study, there is no between subject effect, only within subject. So, do you think the assumption of a common slope, in other words, a common reaction to sleep deprivation, is valid here? Who thinks it is? Who thinks it isn't? I don't think it is either. Different people are reacting differently. Some people had no problems, some people had major problems. So all the random intercept does is allows people at baseline to randomly vary. It doesn't allow that type of behaviour. So, representing our model in terms of this data, we have reaction time equals beta 0 plus beta day plus subject plus error time. Now just note, I'm actually treating day as a continuous covariate here. It doesn't really matter. It's a much less expensive model. I'm assuming it's a linear relationship. That's the only problem that I'm imposing. That's the only constraint I'm imposing on that by choosing that. So I'm not making it an ordered factor or anything. It's a continuous variable. So rearranging that around, we have reaction time. We have the average intercept. And then we have the subject-specific change from that average intercept due to who they are. Some people are going to start with lower reaction times. Some people are going to start with higher reaction times. And then here's the standard beta day. Here's the standard day effect. That's a normal fixed effect. Normal fixed effect. So here is the R to fit it. So we need the LME4 library, because this does not come with R. So we need the LME4 library, which I'll get you to install later on. Now, unlike generalized linear models and general linear models, we actually need a null model, a model with nothing in it, to see if our model improves on that null model. So before anything, we fit a null model. So we have a linear mixed effect regression. That's what LMER stands for. Reaction time, squiggly line, 1. That means intercept only. Plus our random intercept model. Okay, that's how we will say our random intercept. And remember, our random effect is subject. And then where to get the data from. Okay, so that's our null model. Our random intercept model is exactly the same, but now we're putting the day's effect in. Okay, so I'll just show you what that means in terms of the model. That is the null model, and that is my random intercept. So now we're seeing, does adding day have a significant effect? That's the question we're asking. So we use the ANOVA command, and we're saying, does the random intercept model significantly improve on the null model? And it will give me a likelihood ratio test. And then I'll ask for the summary of the random intercept model, as I did with the other models. And I get results that look like this. And we see, now there's two things we need to notice here. The first is the likelihood ratio test, which gave us a chi-square value of about 116.5 and highly significant. Notice it only had 1 degree of freedom because this is actually a continuous variable, the day's effect. Okay? And the other thing to note is the change in the AIC. Okay? We're no longer dealing with nice models. We don't have R squared values. So our only way of gauging model improvement, besides significance, is in terms of parsimony measures like AIC. Okay? And just remember, low AIC is a good AIC. More to the point, a lower AIC is a good AIC. Because the value itself, the absolute value of AIC is meaningless outside of the context of this data set and this model. Okay? So that's a substantial reduction in AIC. That means a much better model. In terms of the fixed effects themselves, there's my average intercept. Sorry, you may not be able to see that from there. My average intercept is 251, and my day's effect is 10.46. Okay, now where does the random component come into this? Normally we don't actually spend too much time looking at it because it's a nuisance effect we want to get rid of. But I do want to look at it in one respect. I want to see how well this model represents reality. Okay, before I do, I'll just talk about the model. We can see from the output that it was a significant improvement on the null model. In other words, the day's effect is a significant effect. When we go to the coefficients table, we see that beta day is 10.46. That is for every extra day of sleep deprivation, we see an increase of 10.46 milliseconds on average in reaction time. We're interpreting that as we would with any other regression coefficient, linear regression coefficient. So again, note that there's no R squared with linear mixed models. They just don't behave themselves in that way. So we have to use AIC. And it's less friendly. But we do note that the AIC is substantially lower for our random intercept model than it is for the null model. And just remember, a lower AIC is a better model. The average intercept was 251. So in other words, at baseline, on average, reaction time was 251 milliseconds. So our random intercept model is going to allow individuals to vary from this average random intercept. So let's have a look at it. Here's our random intercept model. Here's our fit, in other words. There's our data. That's reality. What do you think? Realistic? Do you think it's realistic? No, I don't. The thing to note, of course, is that these random lines are a normal distribution around the average regression equation, and they only change in their intercept. Hence the name random intercept model. So I don't like this model. I don't think it's very realistic at all. I think we need to go a little bit further. So it doesn't seem to fit the data well. It appears that the assumption that all subjects have the same slope, in other words, the same reaction to sleep deprivation, is unrealistic. A better model might be the random coefficient model. Now, what's a random coefficient model? It's one where both the intercept and the slope for an individual are allowed to vary from the average regression equation. So, representing our same model, we have reaction equals beta 0, beta day, that's our normal fixed effect. There's our random subject intercept. Here's our random subject effect due to day. In other words, we have a slope that is subject specific. Okay? So, in other words, we have a change in the intercept due to subject, and then we have a change in the slope due to that subject. So each individual can vary from the average regression equation, both in terms of their intercept and their slope. So this is what I'm talking about here. Beta 0 is the overall average Y-intercept. Subject 0 is the change in the y-intercept due to subject I. Beta day is the overall average slope for the day effect or sleep deprivation effect. Subject day is the change in slope due to subject I. Some people deal with it better, some people don't. So in other words, if we think about this in terms of interaction or effect modification, we can see the subject day component as the effect modification of sleep deprivation due to subject I. So running that model, here we just have subject within days. Okay, everything else is exactly the same. Now I'm actually going to compare the random coefficients model, to the random intercept model. Okay, does it significantly improve on the random intercept model? So you can see as I'm getting progressively more complex, I'm seeing, does this more complex model compare well back to the lesser of the two complex models? I can also compare it to the null model if I want. Okay, so comparing the random intercept and the random coefficient model, it appears that, yes, the AIC is going down. Was it a significant improvement? Yes, it was. So the random intercept model significantly improved the fit of the model to the data. And P is less than 0.0001. And again, now an important thing to note, and I was talking about this to someone before, is an important thing to note, is the fixed effect estimates don't actually change. They're exactly the same. They're actually exactly the same. Still 251.4, still 10.46 for the slope. And you may not realise, but it would also be the same estimates had I fit a standard linear regression to the data. The betas do not change due to correlated data. The standard errors change due to correlated data. Remember, we will underestimate standard errors if we do not take into account repeated measures data. Remember I talked about the blood pressure example before. Okay, so first we note that the random coefficient model represents a significant improvement over the random intercept model. But we have to ask the question, was the extra model complexity worth it? The AIC, which takes both fit and complexity into account, says yes, it was worth it. It was still lower. And as I said, we should note that the betas don't actually change. The estimates of the betas don't change in random intercept, random coefficients, or straight fixed effects models. In other words, straight cross-sectional models. It's all exactly the same. Okay, it's standard errors that change. Finally, let's see if it looks like a better fit to the data. What do we think? I would say it's better. It's a better fit to the data. Anything you think that we could do to improve? Which I'm not going to do, but any guesses? My feeling would be to consider potentially non-linear effects. Not that I want to do that now. Because you can see some people, they're sort of peaking in their reaction time and coming back. Others, not much is happening. Some of them are quite flat, and it's just natural variation. But a couple of them are peaking and then sort of coming back again. I don't know if they're sneaking some sleep in. But I might actually consider some non-linear effects. Whether I should do that in the fixed part or the random effects part is another matter. My feeling would probably be the random effects part because the linear model seems to be fine for some of them but not the others. Okay? But anyway, I'm going to leave it there for that. Okay, I want to very, very quickly cover sample size. Like many of the other methods, and I understand that you haven't covered too much on sample size calculation, but we can also calculate sample size for this when we have a single between subject and a single within subject effect. For more complex models, we have to go back to the rules of thumb type models. Rules of thumb type approach to calculate our sample size. We only need one additional bit of information when calculating the sample size above what we normally need, and that is an estimate of the within subject correlation. We often don't have this because this is prospective, so we usually have to guesstimate it. I go into a little bit of detail about within subject correlations when we get to the marginal model, but in the meantime, I'm just going to give you that simple definition I gave you before. Within subject correlation is the extent to which measures taken from a single subject are correlated over time, over space, it doesn't really matter. And I gave you the example of white blood cell count before. So here is the formula for sample size calculation for a linear mixed model. This, in fact, if you take out one or two terms here, like this part here, and that, it's a standard two-sample t-test calculation. So there's just one or two things that are being added to it. First, how many time points are we considering? That's capital T. And second is within subject correlation. So I just have to ask a question here. So you have or haven't done much sample size calculations? You seemed unsure of it before. Have you done sample size calculations for a two-sample t-test? No? Yes? Yeah. Proportion and not two-sample t-test, like a standard? Okay, no, that's okay. Because if you are familiar with that formula, you can actually see it's a simple simple extension, particularly if you've done it for clustered samples before, because this is really just a combination of a couple of different other formulas. Okay, in which case I'm not going to go into too much detail, except if you haven't covered sample sizes before, I probably won't talk about it at all. So let me see what I say about this. I might actually skip this, okay? And what I'll do is, I'll get you to have, anyone who's interested, get you to have a quick look at it during the break, anyone who's got questions about it. Because we are running very short on time. And sample size calculation, if you haven't sort of done it for the standard situations, I don't want to jump into the basics of sample size calculation in terms of the linear mixed model. Definitely not. Okay. Probably not. I would have to look at that formula because cohort's a more general word. Well, I mean, it basically just means exposure precedes the outcome. And that's not going to take into account how many time points you have. Okay? So I would think not.
Can you just take 5 minutes on this one?
Yeah? This one here?
Yeah.
Okay.
Our students have learned about sample size.
Okay, they just forgot they have. Okay, so what I'm going to do is I'm just going to use the autism data as a very quick example here. Okay, so remember the outcome was level of socialization. We had a within subject effect, which was age, and we had 5 time points. So capital T is going to be 5. We had a between subject effect of their communication skills at 2 years, and we had 3 groups. So we have 3 between subject groups here, low, medium, high, and we're used to thinking about the 2-group case, but it's really simple. We just multiply the number per group by 3. It's very, very simple. Okay, so the way I normally talk about sample size is I give you the 4 ingredients of standard sample size calculation. Okay, so I've sort of gone through it quite quick. The no-brainers, the ones we don't have to think about, is alpha, a type 1 error rate. What is it? Always 0.05. Almost always 0.05. Okay? With power, what do we always do? We choose 90, see that we don't have that many patients, and then go back to 80. That's what a lot of people do. But let's just say we can manage that 90%. Because two values are used by standard values are used. 90% power, 80% power. What do I mean by 90% power? Can someone interpret that for me? What's 90% power mean in reality? Nine times out of 10, well, I should say 900 times out of 1,000, what will I do? Detect a difference? Let's say a true difference between the two groups, because we're not talking about false differences. That's right. Think of it as the true positive rate, okay? So when I say 900 out of 1,000, what I mean is after a large number of times, you know, laws of large numbers. So 900 times out of 1,000, I'm going to detect a difference that is truly there, okay? 10% of the time, I'm going to fail to notice it. So a false negative. That's the type 2 error. Okay, so type 1 and type 2, we usually don't have to think about those things. Standard deviation, pilot data, backed by previous studies, suggests that we would expect to see a standard deviation for a certain age, for a certain language group, of about 15 units. Standard deviation in this VSAE, I think that's what it was. It's basically the socialization value. Okay, so how much that feed into their social network and so on. Okay, that can be tricky to get. A lot of the time people will estimate that too. Or they'll go to literature which is reasonably relevant, but not that relevant, or they'll get expertise. This is one. Now, if you are unfortunate enough to get a lecture on sample size by me, I will tell you this about 10 times. I don't think this audience is going to be a bad one. The clinicians that I usually lecture about sample size, I want to shake them and say, listen to me. Okay, minimal clinical difference. Consultation with experts suggests that a difference in socialization less than 10 would not represent a scientifically important difference. Now, why do you think I want to shake those poor clinicians and say, listen to me? What do you think clinicians will often do rather than choose the minimal clinical difference?
Choose the maximum.
No, not choose the maximum. No, not choose the mean at all. They just go to another study and say, oh, Smith, 2010, saw a difference of 5.3. They observed a difference of 5.3. I'm going to say that's my minimal clinical difference. Minimal clinical difference is a scientific quantity, not an empirical quantity. What do I mean? What do I mean by that? It's a scientifically important difference. It has nothing to do with what Smith observed, which may or may not be important. Okay? Sorry, I can't go into any more detail about this, and I think the 5 minutes talk on this is probably unrealistic. So it's got nothing to do with data. Well, it's got to do with previous experience. It's got to do with experts. Now, there's two reasons clinicians won't do this, that they'll go to previous research and look at empirical differences. One, they don't understand the difference between scientific difference and statistical differences that have been observed. Okay? The whole point of prospective powering is to align clinical difference with statistical difference. When P is less than 0.05, there is a scientifically important difference between my two groups. That's the most important value that goes into this calculation. So that's the first reason. The second reason is confidence. They don't feel confident with coming up with a number. They will doubt themselves about it. And this is why we'll talk to experts and so on. Okay, anyway, I'm lecturing on this and I shouldn't lecture on it. Okay, so these are the things that we would normally put into a sample size calculation, right there. The things that are specific to longitudinal data is T. In this study, we are considering 5 repeated, that's supposed to be, measurements. So 5 time points, so capital T equals 5. And this is a bit of a trickier one. We have the within subject correlation. In the absence of knowledge, because I don't have any data yet, I'm going to say that there's a moderate level of within subject correlation, and I'll set it at 0.6. A rough guide that people will often use is if we think it's quite weak, we'll use 0.3, 0.6 for moderate, and 0.9 for strong. So plugging all of this in, and just remember with sample size calculations, it's arithmetic. If you set out all of the values you need, well, on the page, it's arithmetic. Nothing more complicated than squaring, multiplication, adding. That's it. It's very simple. It's one of those, people think it's a dark art and that it's complicated. Sample size calculation is so simple. Okay, so where do these values come from? I haven't talked about it at all. They just come from a normal distribution, a standard normal distribution. So there's our magic 2 standard deviations from the mean. Is 95%. It's not actually 2, it's 1.96. So that's for my type 1 error, that's for my type 2 error. They come from the normal distribution. I put it in here. There's my 5 time points, my correlation of 0.6, my 5 time points, my 10 units of minimal clinical difference, and the standard deviation. So I'm really just plugging it in, and I come out with a value of 32.13, or 33 children that are needed for each group. So I have 3 language groups times 33 children, so that means 99 children. 99 observational units. How many observations? About 500. Okay, so 99 or 100 observational units, children who will be observed 5 times. So what I'll do is I'll just leave you to look over that yourself. I just show you what you would get if you did it in a cross-sectional study. Okay, so where to from here? There's one more model that I actually want to consider when it comes to a continuous outcome, and that's a linear marginal model. And I'll just start that in a minute. So this is supposed to go at the end of last lecture. And I say normally that I would stop here because I'm scared of your brains burning up. But I know you're stronger than that. So we are going to go straight onto the marginal model now, which I'm not actually going to suggest you use. You can use them. They really give you pretty much exactly the same results. I just like mixed models. And I'll go into a little bit more detail about why I like mixed models at the end of the next section. Why am I covering marginal models at all? Because of GEEs. Generalized estimating equations are marginal models, and they are widely used. Not by me, but by others. And at the end of the next session, what we'll do is we'll have a break and we will get into our... Okay, so I'm really going to go straight on to the next session, so 5-minute break. Don't even leave the room break. Stand up and stretch break. What time was the demonstration? Okay. I can't get through most of this one. This is actually not as long as this one. Okay, so I'm just going to go straight into this one now. So as I've mentioned before, I'm going to talk about marginal models now, which is a different way of thinking. And because you will normally have had an hour's break between these two lectures, I would spend a little bit of time actually revising the linear mixed model, but I'm not actually going to do that now because you covered it about 5 minutes ago. But remember what we're doing. We're dealing with models that deal with continuous correlated outcomes, repeated measurements data. The mixed model is conditional. It's called a conditional model, and it is subject specific. What do I mean? Every person has their own model. They have their own intercept at the very least, and if we use a random coefficients model, they also have their own slope. And we covered the two types, the random intercept and the random coefficients model. So now we're going to talk about the marginal models. Okay, so remember when I first introduced this, I said these models, both mixed models and marginal models, deal with this problem of correlated data by putting something here, putting something at the end, and I mentioned that mixed models use extra coefficients at the subject level, okay? And marginal models have this habit of throwing things into the error. Put the problem into the error term. That's what marginal models do. Okay, so by specifying the right error structure, we can deal with this correlated problem. Now there's an assumption when we do that. We're assuming all subjects tend to behave much the same way, that they correlate much the same way. So here, I've already covered this. Remember I talked about the conditional model, or the subject-specific model. With the marginal model approach, the basic idea is to throw everything into the error. This allows marginal models to deal with the problem of correlated data. But not all data are the same. The patterns of variance and covariance or correlation might change a bit. And for this reason, there's a couple of different types of errors or error structures we can actually specify to account for this. It's sort of a nice way of doing it. It is a nice way of doing it. And I did mention one to you before already, the compound symmetry one, which was, doesn't matter what the time is, the variation should be the same, but also the correlation between times is assumed to be the same. Okay, so I'm going to jump straight into them. The first error covariance structure, or residual covariance structure. Now that's a big word, but what does it mean? It means the first error term that we're actually going to say, it looks like this. This is the structure of the data error. Okay? The first one and the simplest one, and it's so simplistic, we don't use it for correlated data, and that is the cross-sectional models error structure, which is just called independence. Okay, so what I'm going to do is I'm going to talk about this again in terms of our autism data. Okay, we have 5 time points. We assume that the variance in socialization is going to be the same for children who are 2 years old. In other words, they vary much the same as children who are 3 years old. So in other words, the variance is about the same size at a given time. That seems okay to me? That's fine. What's unrealistic about the independent covariance structure is that the correlation between 2 years and 3 years for a given subject is 0. In other words, someone's socialization score when they're 3 years old is independent. It's not correlated at all with what they are at 2 years and so on. Is that realistic? Not for repeated measures data, definitely not. It's fine for cross-sectional data, but it's not, okay? So that's the simplest type of structure that we could use, which we would never use for repeated measures data. It's too simplistic, and particularly this assumption that the data aren't correlated. So in other words, to model my correlated data, I'm going to use a model that assumes the data aren't correlated. Not very realistic. What's the advantage of it? It has one parameter estimate. Sigma squared, the variance. So it's cheap, at least. So as I said, the variances at each time are about the same. That's realistic. But the assumption that they're independent, no, not at all. Okay, so let's now move to the absolute other end and go to the most complicated one, and that is unstructured. This structure makes no assumptions whatsoever about the nature of the correlation. In other words, variances at each time are allowed to be different. Correlations at each time, or between times, are allowed to be different. So, a different variance at each time, and every between time correlation is allowed to differ. This is actually, and I mentioned this very briefly before, this is actually the error covariance structure, or residual covariance structure, that underpins the repeated measures MANOVA. Why is repeated measures MANOVA a problem? Because of the missing data issue. We can fit it in a marginal model and we don't have that same problem. It makes this model very, very expensive. For 5 time points, we need 5 values for the different variances to estimate, because remember, we're allowed a different variance at each time, and we need another 10 covariances for time 1 verse 2, time 1 verse 3, time 1 verse, you get the idea. So just for 5 time points, we need 15 additional parameters. Still cheaper than a mixed model. But there's also one distinct advantage of this covariance structure. It gives us a good picture of reality. Okay? By it not being structured at all, its estimate of the covariance structure should be quite realistic. It might be overfit, but it's realistic. So what will it look like? Something like this. So the variance at time 1 is different from time 2, different from time 3, different from time 4, different from time 5, and the covariance 1 and 2 is different from 1 and 3, and so on. So in other words, there's our 15 different values. It is a symmetric matrix. In other words, the covariance between 2 and 1 is assumed to be the same as 1 and 2. That's fine, of course. Okay, so very expensive, but gives us a good estimation of reality. So even if I don't use it, I will always estimate it to see how well my model will fit. I'll give an example of what I mean by that soon. I estimated, just by looking at it, I can say, oh, compound symmetry would be fine, for example, because all my variances were equal, all my covariances are equal. So compound symmetry is probably okay. Compound symmetry is the next one, and sometimes called exchangeable. So it's a type of residual covariance structure, and we think of it as a compromise. Like the independence covariance structure, variances at different times are assumed to be equal, but unlike the independent residual covariance structure, observations over time are allowed to be correlated. There's a problem. They all have to be correlated in exactly the same way. I mentioned this in the last session. The correlation between time 1 and 2 has to be about the same as time 1 and time 3, time 1 and time 4, and so on. In other words, it doesn't matter how many time points there are between values, the level of correlation should be about the same. probably relatively unrealistic. The advantage, only 2 parameters are needed to be estimated, unlike the unstructured. So it's relatively cheap. And you can see how this works. The more simplistic you get, the cheaper the model in terms of fitting it. The more realistic it is, the more expensive it gets. And we need to find the best compromise. And compound symmetry is the error covariance structure that underpins repeated measures ANOVA. So if I run a linear marginal model with the compound symmetric residual covariance structure, I'm really sort of running a repeated measures ANOVA, or something very similar to it. What does it look like? Equal variances at the different times and equal covariances regardless of how many time points before. It's the simplest structure we can have for true repeated measures data. And it's been used for a long time. Not explicitly, implicitly, but it's been used for at least 50 years, probably longer than that actually, but it only requires 2 parameters. One last one I want to talk about is the first order autoregressive one. Also a 2-parameter residual covariance structure. It differs from compound symmetry in that it allows between time correlations to decay. In other words, further apart points are allowed to have a smaller correlation than points that are close to each other. That's nice and realistic. It is assumed that this decay follows a particular formula. Okay, that there's sort of an exponential decay in that. It's a sensible structure to use when we have evenly spaced time point studies. 0, 1 week, 2 weeks, 3 weeks, 4 weeks. It will often work relatively well there. It also has 2 parameters, so also quite cheap. Just to show you how it works, equal variances at the different times, but you can see here's our correlation coefficient here within subject correlation, and that value is squared when there's 2 values. So there's a point separating the 2 values, 2 points separating values, 3 points separating values. So as you square a number that's below 1, it's going to get smaller and smaller and smaller. Square it, cube it, take to the power of 4 and so on. So you'll see an exponential decay in this. So I think the thing to note that the time points should really be equidistant or close to equidistant for this type of structure. But again, have a look at the unstructured and see if that represents a realistic picture. So how do we choose? I've covered 3. The first one, the independence one, there's no way we would pick that. It's unrealistic. I've covered 3. Unstructured, compound symmetry, and autoregressive. How do we choose which of those 3 or some hybrid between them? And there are different ones. Other than those are the 3 main ones. How do we choose which one? In an ideal situation, we can be guided by the study design. So if we have equally spaced time points, an autoregressive might be a good choice. However, if it's not clear by study design, we need to be a little bit empirical about it. We need to look at the data and see what it tells us. Now there's 2 ways we can do that. First, we can look at the unstructured residual covariance matrix. That gives us a picture of reality, okay? By estimating that, we can actually see what the true residual covariance structure is likely to look like. The other way is to fit, for example, all 3 and see what the AIC tells us. Lower AIC is better, remember. So, as I said, 2 aspects: model fit, number of parameters, how expensive is it? So we'd use something like an AIC to gauge that, because remember, AIC takes into account both model fit and complexity. It penalises for complexity and it penalises for lack of fit. So we want the model that is best for both of those things. Low AIC. Now, one thing I need to mention quickly before we go on to GEEs is that AIC only works for models fit using maximum likelihood estimation. In a GEE, a generalized estimated equation, we don't use maximum likelihood estimation. We use quasi-maximum likelihood estimation, so we can't use AIC. In models like that, there is a measure called quasi-IC, information criteria, that we can use that works much the same way. Okay, so as I mentioned, there's two things I will do if I run a marginal model. Run the model with the unstructured error pattern matrix to get a picture of the true structure, and then be guided by that. If it looks compound symmetric or it looks like AR1, I will then go and fit that. And to use one of these fit measures or parsimony measures, AIC or QIC, to gauge it. Okay, so just to give you an idea, because I'm not actually going to run one of these, but I just want you to see what it looks like. What I did here is I fit the unstructured matrix to, well, it's actually to a GEE, but it doesn't really matter. Now, looking at that, the equal variances are equal because I've imposed that on it. But what about the correlations between values? What would you say about those? What's happening as more time points get between the values? It seems to decay. It's getting negative, which doesn't really make sense. But if you set these to sort of 0, which I probably would, I can see it decays there, it decays there, it decays there, and so on. I would probably say an AR1 would be a relatively good measure. Okay? Is everyone happy with what I mean? Equal variances and the decay in correlation as we get more time points apart. So in other words, 2 years and 3 years was 0.88, 2 years with 5 years was 0.021. I'd probably assume those to be 0. It was negative. Autocorrelation doesn't really make sense here. And you can see here it's a decay. So I would rule out compound symmetry for a start, which assumes all these values to be equal. I don't think that's valid at all. But I might try the unstructured and the AR1. I wouldn't even consider the compound symmetry. Here are the actual matrices. That's the compound symmetric. You think that there is a good picture of that? Compound symmetric, unstructured? No, not even close. Autoregressive one, what about that one? Now see, even that's not a terribly good fit. I'd probably go with the unstructured there. And only after choosing the correct error structure would I go on to actually conduct the analysis itself and test significance and so on, which should give you similar results to what we were doing before, okay, with the linear mixed model. Okay, so why have I wasted so much time, wasn't that, maybe about half an hour, talking about linear marginal models if I never use them? And people don't use them that much, linear marginal models. The reason I don't particularly like them is, unlike the linear mixed model, they don't present a subject-specific model. They give you a population averaged model. Okay, so there's an average correlation among the data. And that's why we can use a single error structure to represent all individuals, and that's where we get the idea population average. In contrast, the mixed models, which are subject-specific models, we have a model for each subject. I don't really like that, not if it's not necessary. So I don't ever use any type of marginal models. People do, but I personally don't. Why use a marginal model when you can use a mixed model? Even for generalized models too. Okay, so I've made those points well and truly by now, so I'll just leave those there. So where, oh sorry, yeah.
Sorry, from public health standpoint, don't you want to know the effect on the population rather than the subject specific?
No, but that's not the hypotheses we're testing, okay? The hypotheses we're testing is still at a population level, okay? Because that's about the fixed effects. What I'm saying is why make assumptions that the random effects work in exactly the same way. The correlation works in exactly the same way for every subject. Why make that assumption when you don't need to? Remember, we're not usually making inferences about these sides of the equations. It's a nuisance. Correlated data is a nuisance we want to get rid of, okay? We want to take it out, put it over there, whether that's by throwing it in the error term, like a marginal model, or putting it into random effects, as in a mixed model. We still want to put it away from us over there and then deal with the fixed effects, which is our inferences to the population. So public health, clinical, it doesn't really matter. There's still fixed effects inferences. That's what we're interested in. So that's a bit of a different issue, what you're asking, okay? The reason I like a subject-specific model is because it doesn't have to assume things are the same for everyone. I'm not even interested, I'm still not interested in that side, but why impose an assumption that I don't have to? It's still a simplifying assumption, okay? Yep.
How would a mixed model handle the example of the person correlation? So nothing is you can also have a random effect as well.
Mm-hmm. You could do that. What it means is a very interesting question, and notably, out of the software I've been mentioning today, SPSS actually allows you to do that. I don't know if Stata does, and I don't know if R does, and I wonder if that's wise of them. What's it mean? What's it mean to add a subject-specific component and a marginal effect as well in an error covariance structure? What does that mean? We did note before that our random coefficients model wasn't a perfect fit. I don't even know what it means. It would mean to add both of those things together, whether it's valid at all. It may not be invalid, but I think the effects might be subtle. Okay, so that's one of those things I'd have to sit down and think really hard about. Actually, probably what I'd do is I'd get a data set where I knew what was going on and try it around, basically mess around with it. I don't know what it means.
So Stata more realistic model.
I don't know whether it is realistic or it's inadvisable, because you've got to watch out that just because you can do something in software, I can fit a linear regression to a categorical outcome. Should I? No, I shouldn't. I don't know what it means. And I think you're talking about complicated models there, and I'm not sure what the implications are. So it's a good question, and it's not one I have an answer for. Should we use a linear model that imperfectly models the correlated structure? Should we, so that's one question. Should we use a marginal model where the assumption that the effect for everyone on average is the same is invalid? Okay, so both of those arguments can be argued. Should we go very complicated and have both a population averaged effect that deals with the residual of what wasn't captured by my random coefficients? I don't know. I don't even know what that means. Maybe. And really what we're talking about here is a trade-off between fit and validity. Because, you know, yes, we want random errors to come out the other end, in the end, once we've accounted for everything. So, yeah, it's a very good question, and I don't have an answer for you. Because it's a very subtle thing. What do I do if there's a residual correlation coming out of my random coefficients model? Should I fit something at the end and see if it's better? Is it important to do that? I've corrected my standard errors. I don't know. It's a good question. It's also a very tricky question to ask. Thanks for that. Okay, I've forgotten what I was talking about now. Okay. Okay, so now what I'm going to talk about quite quickly, I'm not going to go into the theory of these, actually. I'm not going to give you mathematics of it, because we can really consider these as a generalization, in other words, link functions, etc., of the linear mixed model, we call that a GLMM, and the linear marginal model, we call that a GEE, even though there's an extra step with that. But we can think of it as a generalization. So GEEs can be used for categorical longitudinal outcomes, and they represent the marginal model approach. The generalized linear mixed model can be used for categorical longitudinal outcomes and represent the mixed model approach. In other words, we're talking about fixed effects and random effects mixed together in a single model. There are other subtle differences, particularly between GEEs and linear marginal models, because of how it does its estimation. But the fact is conceptually, this is how we can think of GEEs and generalized linear mixed models. In fact, probably a more meaningful name for a GEE would be generalized marginal model. The guy who named it didn't name it that. Okay, so now, talking about life, the universe, and everything. This is a majority of biostatistical modelling right here. Particularly, let's forget about survival analysis models for the moment, which are very important in clinical work. But if you forget about clinical survival analysis models, this is a large majority of modelling in biostatistics. Right here on this slide, you can do a lot with these four models. So here we are right here. We have correlated Ys that are also categorical. We are now down in generalized linear mixed models and generalized estimated equations. There are other models out there, of course. But this is, if you understand this, you're most of the way there. So as I promised, I'm not going too much into the mathematics of these two models. And I'm just going to present a couple of slides on each. Okay. And then what we'll do is we'll get to running them in R, and then after this session, we get to use R. That's the fun stuff. Also, I'm going to focus specifically on binary outcomes there, but you can also run them for Poisson and multinomial outcomes. And also there's an ordinal linear mixed model, which is technically not a generalized linear mixed model, just like an ordinal linear model is not technically a generalized linear model, but it works much the same way. It just comes from a special library, which I can't remember at the moment. I used it recently. And we will use the respiratory RCT data that we discussed. Remember, respiratory illness, yes, no, was our outcome. We had 2 treatment groups, placebo and active. I think it was 4 time points that we considered in that. It doesn't really matter. Multiple time points. Okay, GEEs can be used to model longitudinal correlated data. They use a marginal population averaging approach, and betas are estimated using quasi-maximum likelihood estimation. In GEEs, the correlated nature of the data is considered a nuisance And like all marginal models, it's just thrown into the error term. Throw it into the error term, deal with it there. As long as I don't have to worry about it, that's fine. Okay? And that's the marginal model philosophy. Just get it away from me, basically. Compared to other models, GEEs deal with the correlated nature of the data in a rather informal way. They use what's called a working matrix. And I actually won't go into too much detail about that. In terms of how we use them, all we do is we specify the distribution and link function as we would with a generalized linear model, and we specify the residual covariance matrix as we would with a marginal model. That's it. That's all we have to do. In fact, if you look at it in terms of this slide, going down this way, we specify a link function and distribution. Going this way, we specify the correlated data structure. That's all we're doing. Okay, so here is my syntax for it. My GEE, note this comes from the library, GEE pack, which we'll download in a minute. GEEGLM, my.y squiggly line, my.x1, my.x2. This is very important. This is our random effect. ID equals ID. Here is the correlation structure. So I'm going to use exchangeable, the compound symmetry. Family equals binomial, and here's the data. You can see all of these are quite familiar, what we're specifying here. And by the way, I'm specifying the correlation structure, and I'm specifying the distribution, and by default, the link function, by not putting anything in there. The canonical link for a binomial is the log of 1. If I wanted to use probit or something like that, I would actually have to write it in. Now, to get my odds ratios and their CIs, their confidence intervals, again, I wrote this function, which I give to you in the long data file soon, so you'll see this. So this will print out the odds ratios and their confidence intervals. Okay, so that's where that is too. Also in that, I have provided a function that someone else wrote, not me, called QIC, which calculates the quasi-information criterion that is needed for GEEs, okay, because AIC doesn't work for it. Okay, so that's also provided. Okay, that's all I'm going to say about GEEs until we get to them when we use GLMMs are a direct generalization of the linear mixed model. To me, they have more mathematical theory and a stronger mathematical justification is probably the word I would use. GEEs are a little bit, oh yeah, it'll do, that's fine about it. Not so much linear marginal models, but GEEs are a little too informal for me. It's sort of like non-parametric tests. Yeah, let's just make simplifying assumptions. Then we won't be specific about our hypotheses. So GLMMs, I think, have a stronger theoretical basis. Again, it's probably one of the reasons I prefer them. In this respect, they explicitly model the contribution of individual subjects in the model. For example, we can specify random intercepts and random coefficients. They're not so readily interpretable for a generalized linear mixed model. Because we're talking about a change in the log odds due to being this subject, and I don't tend to think in terms of log odds. I don't know about you. Unlike GEEs, we aren't restricted to simple data structures. And I'm not sure if I made this clear before, but GEEs work for when we have a single random effect, whether it be nested or whether it be crossed with other random effects. GEEs and marginal models are restricted to very simple data structures. In other words, a longitudinal effect. Now remember, in this study here, we have both a longitudinal effect, so in other words, we have patient ID, but we also have center ID. I could not fit that using a GEE. I have to ignore the center ID effect. I could fit that in the generalized linear mixed model. Okay, so they allow more complex designs. And this is why we would use generalized linear mixed model in a multi-level analysis where we tend not to use GEEs. They're just too simple. So they work to a point, but after that, they don't work very well. So the reason this is because mixed models allow clusters at different hierarchical levels. So repeated measurements of patients within clinics, within provinces, for example. We could fit a data structure in our generalized linear mixed model for that, or a linear mixed model. We can't do it for marginal models, whether they be linear or generalized. Okay, here is the syntax for my generalized linear mixed model. Looks very similar to the GEE. Again, library LME4. Here I'm just going to use a random intercept. GLMER, generalized linear mixed effect regression. My Y, squiggly line, my X1, my X2, plus 1 straight line patient.id. Here's my family, the binomial family, there's my data. Here's my summary function, and again, in order to get my odds ratios and confidence intervals, I have to specify that function there, which I have provided to you. Okay, so let's run a very quick example. We have the data I've been talking about, which is the multi-center placebo-controlled RCT to investigate the efficacy of a drug on respiratory illness. So yes, you have it, no, you don't. And then we have respiratory illness as our outcome. Visit, which is the within subject fixed effect. Treatment, which is a between subject fixed effect. We had 2 random effects. So in this analysis, and this is an important thing to note, particularly with RCTs conducted over time, that we're not just interested in the main effect, the treatment effect, but also the treatment by time effect. Now, don't read this. I want to ask why. Why is that? Why are we interested in the time by treatment effect? Think RCTs. What should the lines look like for the 2 groups in an RCT? A successful one. Let's assume that a Y variable going up is good. So placebo, flat, and treatment group, I'm going to make sure I get the right way around, treatment group going up like that. Okay? Now what happens if I just look at the main effect there? This average is going to come down just due to the baseline values. So it's going to do that. So the main effect is going to include baseline values as well as the later values. And that's going to weaken my effect size, isn't it? So it's actually the interaction effects that is of interest to me in an RCT conducted over time. I want to show that this line increases and that that line stays the same. Basically, that's what I'm saying there. So if the treatment is first administered at base time, we'd expect some sort of lag time before the treatment starts to kick in. And that's going to weaken the effect size if we just throw it into the overall main effect for treatment. So only the treatment by time is going to give us an idea of the 2 groups, or of course post hoc tests conducted at the later times. We could do that too. But that's still the treatment by time effect anyway. Okay, so I'm going to keep our analysis pretty simple here and consider a single within subject effect, visit, and a single between subject effect, treatment, and unlike the previous analysis, I'm going to treat visit this time as a factor Remember with day I treated it as a continuous variable? Now it's actually a factor. So before I do anything, I'm going to convert the variable visit, which is just 1, 2, 3, 4 at this point in time, to a factor in R. So visit.f, so in the respiratory.df, I'm creating a new variable called visit.f, which is a factor of respire.df visit. If I don't tell it that, it will assume visit is a numerical variable. So you have to be careful when you code factors using numbers in R that you let R know that it's a factor. You can do that here. You can actually do it inside the model if you like. Okay, the only problem with doing it inside the model is you have to remember to do it every time. Okay, so here's my GEE. I'm going to use an exchangeable matrix, an exchangeable error structure, outcome, treatment, visit.f, treatment by visit. Notice the full colon is the interaction term, ID equals ID, and so on. Okay? So there's nothing different here. Note there's an ANOVA statement, a summary statement, my confidence intervals, and I also want the quasi-information profile. So we'll just come back to that. Okay, that's what's spit out, and it appears that there's a treatment effect overall, but that's about it. That was, by the way, that's the ANOVA. And when it came to looking at the individual coefficients, again, we don't really need to do the omnibus test for treatment itself because there are only 2 treatments. We know if there's a difference among treatments, we know which 2 it is that different. Okay. And here are the confidence intervals. Now, anyone notice something strange about the confidence intervals for the odds ratios there? And you're going to get this in both GLMMs and GEEs. These are odds ratios. Anything weird? Well, there's 2 things to note, really. The first, the odds ratios don't actually agree with the hypothesis test. The odds ratio said that there were a difference between the 2 treatments. Our odds ratio contains, confidence intervals contains 1, which suggests that there's no difference in the odds between the placebo and treatment groups. But there's something else weird there. What else is strange? Let me I'll prompt you a little bit, okay? I can interpret the odds ratio of 0.44. Can someone interpret the odds ratio of negative 0.33 for me? In English. Actually, even in Thai, if you can manage it. What's a negative odds ratio mean? Technically impossible, isn't it? Odds have to be positive, so their ratios have to be positive. So this is what happens when it comes to confidence intervals for both GLMMs and GEEs. Strange things happen. So we have to be quite careful in their interpretation. My feeling, what would I do here if I was writing this up, is I would interpret the p-value and I would interpret the odds ratio itself. I would leave the confidence intervals out, okay, altogether. There's a disconnect. We're talking about complicated models now. And there's things that work for generalized linear models that worked before don't necessarily hold anymore. Okay, so as I've already said, we can see in this model that only the treatment effect was significant. Only partial evidence that the treatment works. Why? It's that time effect. But the fact that the main effect was significant is, I guess, good news. We should also note that there is a disconnect between the results of the ANOVA and coefficients. It's a significance test. and the confidence intervals. So, okay, I'll leave that. I've commented on that already. Okay, just a note for later, the QIC was 597. Actually, I won't use that because I'm not going to compare different GEEs. Note that I can't compare an AIC from a GLMM with a QIC from a GEE. They're just different numbers, calculated in different ways. Okay, so just out of interest, I went through and calculated the coefficients. Again, note I haven't given you confidence intervals for each of them using the 3 different covariance structures, and I got quite different results as well. So there's the exchangeable, the AR1, and the unstructured. Okay, all of the overall models were significant and so on. The QICs not included. The only difference we see is in these individual terms. Okay? I would probably go and eyeball the unstructured matrix itself, which I haven't included here. Okay, quickly, the GLMM. I know I've only got about 5 minutes left. So now let's go and try a GLMM on exactly the same data. Again, I'm going to use both a random intercept and a random coefficients model. And remember, it's a little bit more complicated to interpret these coefficients when we're talking about a binary regression model, a binary logistic regression model. But remember that we're talking about starting at different values, which is the intercept, and progressing differently was the random coefficients, or I should say random slope aspect. Okay, so here we go here. Library LME4, GLMER, the outcome. We need to fit a null model first, as we did before. And then we go and fit our random intercept model. We compare the intercept model to the null model. This looks very similar. In fact, really, this is exactly the same as a linear mixed model, except for the family statement in there. Okay, we'll get to practice this in the next session. And then I get a summary. Okay, there it is. It gives us much the same result. That tells us that only treatment is significant. We can see that the model represents a significant improvement on the null. We can see that the AIC associated with the random intercept was somewhat of an improvement over the null. And that, only, like the GEE, only the main effect for treatment was significant. I'm not going to talk about the odds ratio until I decide on the final model. So just jumping into the random coefficients model. Remember, this model allows subjects to respond differently over time. So in the context of this study, we can expect patients to improve or worsen of their own accord above the effect of the treatment, and also respond differentially to treatments. What does this mean in a GLMM context? It's much simpler for LMMs for a start. So patients are allowed to have their own departure from the average log odds ratio between visits. If you can interpret that, tell me what it means. Okay, so let's fit that in R. Okay, again, nothing different here. We've got treatment, visit, exactly the same. The only thing that's different this time is the random coefficients effect here. I'm going to do 2 comparisons, the null to the random coefficients model, and also the random intercept to the random coefficients model, and then I'm going to summarize it. Okay, so comparing the random coefficients to the null, we see it's just significant, but comparing it to the random intercept model, we can actually see it's not good at all. Basically, we can see that the random coefficients model actually has a higher AIC, so the complexity was not worth it, than the random intercept model. So my feeling here is we would go with a random intercept model, the simpler model. Okay, so I've already just mentioned that. So first thing, random coefficients model fit the data significantly better than the null model. That's no surprise, the null model has nothing in it. But for the extra model complexity, having the additional set of betas for every patient, which is very expensive in this case, because don't forget, we're not talking about a continuous variable anymore. We're talking about odds ratios of time 1 to time 2, time 1 to time 3, and time 1 to time 4, was not worth it. So we had 3 extra betas for every patient. So the AIC was actually lower than for the random coefficients model. Okay, so in other words, the null AIC was actually lower than the random coefficients model, not only the random intercept. So comparing random coefficients versus random intercept, we can see that it just wasn't worth it. Random intercepts is the answer here. So we had 5 models that we compared, the 3 GEEs with exchangeable AR1 and unstructured covariance structures, and the random intercept GLM and the random coefficients GLMN. Which one would you pick? I know what I would pick. And I wouldn't necessarily be guided empirically by this. There's only one model I'm actually, there's 2 of those models out there. Now the fact that there's 2 of them gives you some information about what I would pick. Anyone got any views? The important thing is they gave all around the same conclusion, that the treatment effect was significant and nothing else was. That's important to know. But which model would you pick? Let's ask the question, do you prefer marginal models or do you prefer mixed models is the first question. And then which of those would you pick? For me, this one. Okay, I will always use a mixed model before I use one of these. And the random intercept we saw fit the data a little bit better. I shouldn't say fit the data, was more efficient at fitting the data. The extra model complexity here wasn't worth it. I would go with the random intercept GLM. And you're not actually wrong to pick one of these. This is a personal preference for me. So I always pick conditional subject-specific models over GEEs. Yes, they're expensive, but they're good. I don't like the assumption of population averaging when I don't need to make that assumption. The problem with when we get to generalized models is we can't actually directly compare these models. I can't use a model that uses QIC and compare it with a model that uses AIC. So when it comes to generalized models, I'm almost left with theoretical decisions, not empirical fit to make my decision. I just don't like to throw things in the air and assume everything will be okay. I like to model things personally. But the argument, again, I have to admit this, the argument against mixed models is they're expensive. They have lots of coefficients. And you could argue that they overfit for that reason. But as we're not making interpretations or inferences about those extra parameters, I don't see that as a problem. It's always our fixed effects that we're interested in, not our random effects. So the question is am I allowed to fit lots of parameters, providing I don't make statements about it? I don't have a problem with that. Okay? If I'm making statements about them or inferences, that's a problem. So I would have, in this case, chosen the random intercept GRMM, but I'm not disagreeing with people who would pick maybe one of the GEEs. Okay, finally, now that I've chosen my model to get the odds ratio, it's as simple as that. And there they are then. And again, we get a very strange value. For a start, this says do not reject HO, we cannot exclude one from that 95% confidence interval. So it's not just GEEs that have a problem here. GLMM, odds ratio confidence intervals get a little bit strange with correlated data. If I was going to report it and it was not significant, I would probably just bring that back to 0. And see we've actually got lots of minuses here. The message here is strange things happen to confidence intervals in the presence of correlated data, particularly when we're generalizing. But probably quite safe with linear models. With generalized models, we're probably not. In fact, we almost know we're not. Okay, any questions? Your brain's too fried to think of a question? Yep. You're going to ask me another tough question, aren't you?
I just want to make, well, I have one question afterwards. Well, my comment is that, in my opinion, I probably wouldn't be choosing any particular model at all, because I think if the relevant question is in testing treatments, perhaps you just want to conclude that the treatment is indeed effective. Maybe you run several comparable models to see whether they go together, whether they're consistent or not, and perhaps just simply report that the treatment is okay, and maybe the odds ratio from each model is similar in value.
Well, they often won't be the generalized because, I mean, you read up on this a little bit. The way we interpret an odds ratio for a subject-specific model should be treated a little bit differently than the odds ratio for a marginal model. They should actually be interpreted a little bit differently. So for a logistic regression-based model, they will be, you can actually get quite large differences. I actually agree with you, except in one point, that we can often be accused of picking the stronger effect. If they agree, I more or less agree, certainly particularly when it comes to significance, as opposed to the magnitude of the odds ratio itself. I would totally agree with you. But I guess it's not something I would mention, say, in a publication, because they will just say, you pick the best one. No one trusts people anymore. Yeah, because people will say, well, you just pick the one with the stronger effect or the weaker effect, depending on what you're trying to sell in your article. Also, the other important point when it comes to the generalized models is they're not directly comparable. One uses a QIC, one uses a AIC. So we can compare within those families, but not between families. It's difficult to do. So I do agree with you that within, I would probably run them both in. But and really, it's almost a subjective thing for me. I like mixed models. I don't like GEs. I know some people who like GEs. I think also one of the things I like about mixed models is we can go that little bit further when it comes to more complicated designs. I shouldn't rule them out. I'm not dismissing GEs. I'm saying I don't necessarily like their philosophy as much. Now that's different from marginal models. So as you mentioned before, with linear marginal models, they're just as valid. They'll give you the same estimates as a mixed model. So that's different. But GEEs have a rather informal approach to dealing with that error structure. Yeah, there it is. Okay.
Just have one minor technical question. Whether you can use the mixed model to approximate the correlation structure, for example, the autoregressive one correlation structure, whether you can actually approximate that using the mixed model, and whether this kind of thing is really even relevant to do.
So you're talking about a mixed model, are you? So you're talking about mixing random effects and fixed effects, but also putting in potentially a marginal component to the model.
What I mean is whether you can just use a mixed model, a purely mixed model to somehow approximate and make a correlation structure that's similar to or like an autoregressive one.
Yeah, I see what you're saying. Probably not. I wouldn't know what that would look like. Because remember, when you're dealing with an autoregressive one, you're dealing with the average correlation structure. So you are assuming that, on average, people in this population between time 1 and time 2 have a correlation of this, between time 1 and time 3 have a correlation of that. No, I don't think so. No, it won't. And I think you'll find that it's, in that respect, probably similar to a compound symmetric model. However, don't forget it deals with the correlated nature of the data through its use of random effects. Now, the question here remains is, could you specify, I think I know what you're saying, not necessarily to come up with a error structure that looks like an autoregressive one, but to deal with the type of things that would result in an error structure that was an AR1. I'm not sure. I would have to think about that because we do have to specify the difference of within subject effects. Sorry, within subject effects, random effects, and then within subject correlation, which all relate to each other, but in a rather subtle type of way. It's an interesting question. And again, I don't have an answer for you. Can we come up with a mold that would be valid if the error structure was, on average, an autoregressive one? I think we'll probably come up with a valid model. But yeah, it's a more complicated question than you think in some respects. One's about within subject correlation, one's about modelling within subject effects and random deviations from that effect due to subject. And how to map those two together, I don't know. Because there's quite a big philosophical difference. Well, I should say conceptual difference, not philosophical. Conceptual difference between a marginal model in that respect and a mixed model. They have very different approaches to dealing with this problem of correlated data. And with linear models, as you pointed out before, they're really both just as valid. You could argue with mixed models, generalized models, that's not necessarily the case. That doesn't mean the mixed model approach is correct. It just means they're quite different approaches that result in differences, even in our beta estimates. Yeah. Okay, thanks.
I'd like to comment on the lower limit of odds ratio that you estimated at minus less than 0. Is that a signal of overfitted model?
I don't think so.
But since you fit the random intercept and random treatment, and the treatment is the interaction between the treatment and time.
It's something we also saw in the GEV,
Yes.
which this is a reasonable sized data set. And I think, which model was I looking at? I don't even think that was the unstructured. I think that was one of the less complicated models that we saw that. My feeling would be is it's not from that, it's from the normal theory that we use to estimate the confidence intervals.
All right.
For an odds ratio.
Yes. So that we assume normal distribution.
That's exactly right. So when we estimate the normal distribution on that odds ratio by exponentiating it, I think that has fallen out. And I'm not sure if any work's been done to deal with it or correct it or to use some sort of alternative to get confidence intervals. Something I need to look into. But clearly a negative bound field confidence interval for
No, it's
uninterpretable. And we certainly couldn't support it.
No.
It just raises doubts in people. I think also the other major point is that our interpretation
from our odds ratio and from our hypothesis test are totally different.
Alright.
The hypothesis test says yes, there's an association. The odds ratio says no,
No
there's not,
association.
or we can't say there is. Yeah.
Alright. Okay. So we have a break
Okay. Yeah.
and we come back.
And
Work
use
on the
R.
data.
Yeah. So we'll come back and use R.
Please take a break about 10 minutes.